We're going to start part 2 here, and let me look to see just how many parts we have. There are 4, so this is a big section here, 4 parts. And we are doing some stuff on our calculator today, so hopefully you've got one. I can put mine up here in a little bit so we can do some of that together. But I'm going to put up here first a rule that we informally, if that's a word, talked about yesterday. It starts out by saying the limit as x approaches c of f of x equals L, that's just your limit, whatever your answer is, if and only if the limit as x approaches c of f of x equals L, if and only if, here we go, the limit as x approaches c from the right, remember the plus sign means from the right, of f of x equals L, and the limit as x approaches c from the left of f of x equals L. L is the same thing here, it's just whatever that limit is. And again, this is something that we talked about yesterday, like the last few examples where there was 3 parts. Part A was the limit from the right, part B was the limit from the left. I told you guys yesterday, if you get the same answer for A and B, then the answer to part C should still be that answer. That's basically what this rule is saying. And the if and only if right here actually means that you can kind of go either way. If both of these limits equal L, then you can assume that this limit equals L. Or if you go the other way, if you know in general that the limit equals L, you can go ahead and assume that from the right it equals L, and from the left it equals L. So if and only if kind of works either way. All right, so what we're going to be doing today is not really discussing continuity too much. We're going to go back to finding some limits. It says find the limit if it exists. May or may not, you never know, we'll have to find out. Find the limit if it exists. All right, I'm going to go ahead and put the first one up here. And it says the limit as x approaches 3 from the left of x minus 3 all over x squared minus 9. That's what we're supposed to find the limit of. Now, it does say that we are only supposed to approach 3 from the left. But according to that rule that we have, even if I'm approaching it from the left, I could still, if I just find the limit as x approaches 3 in general from both sides, it should equal the limit from just the left side. So I've kind of written that out. This is like a bubble here because this is what I'm thinking in my brain. If you want to write this down, it might be helpful. This is what I'm saying to myself. If I can find the limit just as x approaches 3 from both sides, there's no plus or minus with that, from both sides, it will equal the limit as x approaches 3 from the left. And this is also how I would do it if it was coming from the right. Doesn't really matter. If you can just find the limit in general, then it should equal the limit from one of the sides. Okay? So, I'm going to actually rewrite this limit without the minus sign. Let's just think of it in general as the limit as x approaches 3 of x minus 3 over x squared minus 9. Forget that it's a one-sided limit. Do it like you usually would, and if you get something nice, it will equal the limit from the left. Now, direct substitution is always the first thing I try. If I try that here, I get the indeterminate form. 0 on top, 0 on bottom. So looking at your function, what could I try to do? Yeah, this right here is a difference of squares. So let's use our factoring technique to make that an x plus 3 times an x minus 3. Now, cross those out, but don't forget you also have to leave a 1 on top. Now it has turned into just 1 over x plus 3. And at this point, we should be able to plug back in that value of x. So on bottom, 3 plus 3 is going to give you a 6. If the limit as x approaches 3 from both sides is 1/6, then you can assume that the limit as x approaches 3 from just the left is 1/6. So that's kind of what we described over there in our bubble. That's our thought bubble. Okay, any questions about number 1? Sometimes when you see the minus or the plus, you automatically think you have to look at a graph. That's how we were doing it yesterday on all of them, by looking at a graph. But again, 1/6 would be hard to find on a graph. So a lot of what we're doing today is showing you how to find one-sided limits, just not by a graph. Okay, let's try some more here. Now, example 2, we want the limit as x approaches 1 from the left of the absolute value of x minus 1 all over x minus 1. Again, for the time being, let's ignore the fact that it's from the left and just think about, in general, how we would find that limit. If this was just as x approaches 1, I would try direct substitution, but plug a 1 in right there and right there, you're going to get 0 over 0, so that doesn't work. Now, I'm going through all of our other options. We had factoring, but you can't factor anything up there. We had complex fractions, but I don't have anything like that. There's no radicals that I could rationalize. So pretty much there's no other option to do this limit other than by just looking at a graph. I try all of my other methods first because, like on number 1, 1/6 would be hard to find on a graph. But if you can't do it any other way, then that just might be your last resort. So I'm going to type this into my y equals. If you forgot where absolute value is, I will show you that. Oh darn, I had the graph up here for example 4. I'll have to clear it out. I'll put it back up there later. I was trying to be prepared. All right, so on top of our fraction, we have absolute value. Go to math and then write option 1. Because it is setting up bars, or your calculator might set up parentheses, but because of that, you don't really have to put extra parentheses around it. Those grouping symbols will keep all of that together. But I'm going to jump out of that, or if you have parentheses, end your parentheses before you divide by x minus 1. Now this part I do need to put parentheses around because that is a quantity that has to stick together. Now I got to remind myself what direction I'm coming in from. I'm approaching 1 from the left. So find where x is 1, which is right here. As I get closer and closer, to where x is 1, what y value am I approaching? -1. You're riding along the -1 the whole way. So that's our answer for this limit. We would just say the limit is -1. Again, graphing is not something I try first, but there's no other options, then that is something that you can look at. Okay, any questions on example 2? We're looking good here. Let me keep going. This is number 3, and it is a piecewise function. I'll give you a couple minutes here just to write it down. Kind of complicated looking. We want the limit as x approaches 2 from the right, plus sign, from the right, of x squared minus 1 when x is less than or equal to 2, or that second behavior says 2x minus 3 when x is greater than 2. Okay, piecewise functions. You could graph this, and I might show you that here in a minute, but I have an easier way to do this. Sometimes graphing piecewise functions takes a while. That's why I was so disappointed that I had to erase all that on my calculator earlier. But instead of taking the time to type all of this in, here's kind of a shortcut. If you are coming in from the right, remember, first thing we always try in a limit problem is direct substitution. But with this piecewise function, there's 2 different things you could plug it into, and you can't do both of them in this case. If you're coming in from the right, I know that's a little wordy there, but you might enjoy writing that down. It would be helpful later on. Since you're coming in from the right, you can just plug 2 into the second behavior. If you're coming in from the right, you can use the second behavior. If you remember graphing piecewise functions, the second behavior was always the one that went out to the right. So that's kind of what we're doing here. If you're coming in from the right, you can just plug it in to the second behavior. And I'm not sure if I have one today coming in from the left, but you could just do the opposite. If you're coming in from the left, you would plug it into the first behavior. Because if you remember graphing piecewise functions, the first behavior always went out to the left. I put up there also, you could just look at the graph, which we might do here in a minute. But for this problem, I'm coming in toward 2 from the right. So I'm plugging that into the second behavior, and this is a really nice shortcut because all I have to do is take 2 times 2, which is 4. 4 minus 3 is 1. So that would be our answer for number 3. I'm going to hold off on graphing that one. I want to show you number 4 instead. But again, if you'd like to just type it in, just check yourself. If you come in toward 2 from the right, the y value that you're approaching is 1. Okay. Now, with number 4, it's not going to specify right or left. It just says as x approaches 1. And as you guys type that in or write that down, I'm going to type that in so I can show you what the graph looks like. But you can still kind of use that shortcut here. It's just a little bit different because it doesn't say from the right or the left. So maybe I'll show you the shortcut first. Give me just a minute though to finish typing this in. All right. Now, for the last problem, I was coming in from the right. So I just plugged it into the second behavior. On this problem, there's no plus or minus, so I have to come in from both sides. And if you want to use our little shortcut for this type of problem, since you're coming in from both sides here, for the shortcut, you would have to plug the 1 into both parts. That's the first thing to do. Plug that number into both parts, or both behaviors. Now, the part in parentheses here, when I put something in parentheses, it almost seems like it's not as important, but actually, it is very important here. When you plug that 1 in, the limit that you get from the left and the right, L and R, left and right, should agree with each other. I'll explain more about that once we actually do it. But we're going to plug the 1 into both parts, and whatever you get from the first behavior, from the left, should equal what you get from the second behavior, which is from the right. Okay, so let's try that. This is me doing the first behavior. I'm plugging the 1 in right there for x. 1 squared plus 1, that's going to give me a 2. Whatever I get from the left or from the first behavior, it should equal what I get from the second behavior. So here I go, plugging in a 1 right there for x. Negative 3 times 1 is negative 3. Negative 3 plus 4 is 1. It says the limit from the left and right should agree with each other. When I say agree with each other, I mean that they should equal each other, and they are not equaling each other here. So we would have to conclude that the limit as x approaches 1 does not exist. If it just said from the left, that would be my answer. If it just said from the right, that would be my answer. However, from both sides, they should be the same. So if they were both 2's, your answer would be 2. Or if they were both 1's, the answer would just be 1. And again, feel free to graph it if you want to just check yourself. I hope I typed this in right. I think I did. As I approach the x value of 1, coming in from the left, it's swooping up here toward the x value of 2. That's what we found out using our shortcut. And from the right, it's coming in toward the x value of 1. It's definitely not approaching a single y value, so you can confirm if you want on the graph that it does not exist. Alrighty, any questions about that? Use the shortcut, that usually helps a little bit. Now for the last part of the lesson here, I'm going to introduce the greatest integer function to you. We saw a graph of it in the homework last night, but we haven't really talked about it yet. So let's find out a little bit about this function. We use this function a lot with limits, or we see it a lot with limits. So I'm going to put just the parent function up here. It's got some pretty fancy brackets. It's like an extra little line in there. But anytime you see those fancy looking brackets, that means greatest integer function. Now, we really have to understand how that function works before we can find any limits with it. So the whole purpose of this slide is just to kind of show you how it works. All right, this is very important. It's almost like the definition of a greatest integer function. When you see those brackets, it means that you want the greatest integer less than or equal to x. Now x is just whatever number is in there. So you're trying to find the greatest integer, the biggest integer, less than or equal to x. Well, first of all, we need to kind of remember what integers are. If you need to write this down, you can. I'll probably erase this here in a second. But integers go on forever. They are negatives. 0 is an integer. Positives, those are all integers. But the main thing is there's no fractions or decimals. It could be 0. It could be negative, it could be positive, but again, no fractions or decimals. It's just the number itself. So greatest integer less than or equal to x. I want to take just a minute here to practice finding the greatest integer with some different numbers. So if you want to write this down, you can, but again, this is just kind of getting us started here with this function. Let's say I've got a 4.02. I want the greatest integer less than or equal to 4.02. What would be the biggest number, integer, less than or equal to 4.02? 4. All right, let's keep going. What if I had a 3.99 in there? What is the biggest integer less than or equal to 3.99? 3. Sometimes you feel like you have to round that up, but again, it's the greatest integer less than 3.99. You can't say 4. 4 would be bigger than that. I'm going to keep going with just a few more here just to make sure we understand. Now, if you put an integer in here, it could be less than or equal to 4. So we're just going to say 4. That would be the biggest number, less than or equal to 4. And starting with negatives down here, sometimes the negatives throw us off. So let's try like a negative 3.99. What would be the biggest integer less than or equal to negative 3.99? Negative 4, yeah. Can't say negative 3. Negative 3 would actually be bigger, greater than negative 3.99. I'm just going to do one more up here for fun. What would be the greatest integer less than or equal to negative 4.02? Negative 5. Yeah, it's close to negative 4, but it has to be less than or equal to that, so that's a negative 5. Now, I want to show you a picture of what the graph looks like for a greatest integer function. You don't have to write this down, so don't waste your time doing it. But a lot of times we call it the step function just because these look like steps going up. And if you kind of think about those numbers we were working with earlier, for example, the greatest, maybe I'll go up here, the greatest integer less than or equal to negative 3.99, this is your x value, is negative 4. If you go to where negative 3.99 would be, you're down at negative 4. You continue to be at negative 4 until you get to the x value of negative 3. The greatest integer less than or equal to negative 3 is negative 3. And it continues to be negative 3 until you get to the integer negative 2, and it jumps up. So again, it's kind of like a step function. That's just how it works. Okay, so let's go ahead, and I think I actually only have one example of these, but let's go ahead and try a limit problem with a greatest integer function. It's a little bit different here, so make sure you're following. Don't work too far ahead. We got to find the limit as x approaches 3 from the left of 2 times the greatest integer of x plus 1. Again, the greatest integer function makes the limits work just a little bit differently. So instead of just plugging in the 3 right here, which is what we usually do with direct substitution, we just plug it right in. Because it's in steps and it's a little bit more complicated, we're not just going to plug in 3. I've got one more thing over here that might be helpful to write in your notes. A lot of times when we do stuff in here and I explain it, it makes sense while I'm explaining it. But when you go back to look at it in your notes, you're like, I have no idea how we got that. So hopefully these little things off to the side here will help with that. It says, since you're coming in from the left, since you're coming in from the left, don't just plug in 3, plug in a number really close to 3 on the left. I'll explain that more once you get that copied. Since you're coming in from the left, plug in a number really close to 3 on the left. Can't just plug in 3. It kind of works differently. Now when I say plug in a number really close to 3 on the left, I always kind of picture a number line. You don't have to write this down necessarily, but I don't know, if I've got a 3 here, a 2, oh, hello, smartboard. Okay, it's flashing lights at me. 2, okay, we're back. 2 and 4. Think about a number line real quick. If you plug in a number really close to 3 on the left, pick any number on a number line that would be really close to 3 on the left. So like a 2.999 or a 2.99 or even 2.9 would work. But basically it's a number really close to 3 but a little bit smaller than 3 because we're coming in from the left. Okay, doesn't matter how many 9s you put here, it'll still work the same way. But let's first of all figure out what is the greatest integer less than or equal to 2.999? 2. So we're going to turn that into a 2. No fancy brackets anymore. We actually took the greatest integer of it. We got back a 2. So 2 times 2 is 4. 4 plus 1 is 5. That would be our limit. If we were coming in from the right, I would have plugged in like a 3.1 or 3.01, something like that, and I would have gotten back a 3 right here, and then I could just simplify. So it depends on which direction you're coming in from. Any questions about how that works? All right, I think that is our last example here. So this should be C22 here. From page 96, we are doing 7 to 14 and then 17 to 21. However, you can skip number 11. Don't worry about number 11. Again, with the one-sided limits, you can try it like a normal limit first, but if that doesn't work, you can always try to graph to help you figure it out.